Hello everyone, I'm honored to be here today to present our work titled Learning from the Past, Adaptive Parallelism Tuning for String Processing Systems. This is a collaborative effort between ByteDance, China Normal University, and University of New South Wales. String processing systems such as Apache Flink and Timely Data Flow have become essential for managing and analyzing real-time data streams in modern applications. These systems rely on a directed acyclic graph (DAG) as a computation model to organize workflows. The nodes in the DAG are operators, and the edges represent dependencies between operators. To ensure efficient execution, a critical aspect is setting the degree of parallelism, the number of instances with which an operator executes in parallel. However, tuning parallelism is challenging. Choosing a small degree of parallelism risks introducing backpressure, where downstream operators cannot keep up with the data flow. On the other hand, large parallelism with computational resources. Manual tuning, as you may imagine, is both difficult and inefficient, especially in scenarios with fluctuating source rates and unseen workloads. Moreover, existing parallelism tuning also links mechanisms to fully use historical execution data and insights from DAG structures, resulting in suboptimal configurations. This brings us to the central question that motivated our work. How can we tune the parallelism efficiently, balancing resource utilization and system performance while addressing these dynamic challenges? The problem can be formalized as, given a historical dataset of execution histories and a target streaming job with its DAG, we aim to determine the minimal parallelism degrees required for each operator to ensure backpressure-free execution. In this work, we propose a new tuning framework, String2. At the core of String2 lies a hybrid framework that combines two critical phases, pre-training and fine-tuning. In the pre-training phase, String2 uses historical execution data to train models that learn generalizable insights about string processing DAGs. More specifically, DAGs are grouped into clusters based on graph edit distance. For each cluster, we train a GNN-based encoder to predict bottleneck tendencies, and thus introduce structural properties in the encoder. This phase enables String2 to capture global patterns in streaming workloads. In the fine-tuning phase, String2 performs cluster matching and refines the pre-trained models using real-time feedback. The pre-trained encoder is augmented by a lightweight prediction layer that dynamically adjusts to workload. This phase is iterative, continuously improving in predictions. In String2, the GNN encoder serves as the core behind understanding operators and their relationships in the data flow DAG. Each operator starts with a basic feature vector. The GNN enhances these features by iteratively aggregating information from neighboring operators in the graph, allowing it to capture both local behavior and larger structural context. By the end of this process, each operator is represented as a rich embedding that reflects not only its own characteristics, but also its role in the overall job. These embeddings enable String2 to accurately predict bottlenecks and recommend parallelism degree. Please note that for each operator in the DAG, the initial feature vector is constructed by embedding static attributes of the operator. These attributes are shown in the table, include type-related features, resource usage metrics, and topological features. We employ a parallelism-aware update strategy to incorporate candidate parallelism into embedding. The operator representation is updated by combining the original fixture vector, and we utilize binary cross entropy loss function to change an encoder with labeled operators. As mentioned before, a bottleneck arises when an operator struggles to process incoming data at the required rate, causing delays and triggering backpressure that affects upstream operators and hampers overall system performance. Accurately identifying bottlenecks is vital for effective optimization. String2 identifies bottlenecks based on resource utilization metrics and backpressure analysis. Every operator in the data flow DAG starts with an unlabeled status. If no backpressure is detected at the job level, all operators are labeled as non-bottlenecks. When backpressure is observed, String2 identifies operators under backpressure that do not have downstream operators exhibiting backpressure. For these operators, it also examines resource usage. If an operator's resource usage exceeds a predefined threshold, for instance, if the CPU load is greater than 90%, the operator is labeled as a bottleneck. Otherwise, it is labeled as non-bottleneck. Upstream operators under backpressure remain unlabeled since their altered data rates make accurate classification inconclusive. This method ensures accurate bottleneck identification by focusing on individual operators' capacity to handle their workload without being overly influenced by upstream dynamics. Finally, during online fine-tuning, bottleneck predictions are refined using a monotonic constraint. This constraint captures the expected behavior of operators. As their parallelism increases, their processing ability improves. By embedding monotonicity into the model design, we ensure that parallelism recommendations align with system realities. We selected SVM and XGBoost as prediction models because both enforce the monotonic constraint, which ensures logical consistency in bottleneck predictions. SVM classifies data by performing a linear segmentation on a hyperplane. It can be adapted to include constraints that directly enforce monotonicity in the dimension of parallelism. XGBoost, as a scalable decision tree-based model, is modified to build tree splits that complete with the monotonic behavior. Next, we introduce the graph at distance-based clustering part. In String2, we use graph at distance as the similarity measure to cluster data flow DAGs. GED calculates the minimal number of edit operations, such as adding, removing, or modifying nodes and edges, required to transform one graph into another. To tailor GED for data flow DAGs, we introduced two additional edit operations specific to string processing: operator type modification and edge direction modification. One of the key advantages of GED is that it satisfies triangle equality. This ensures logical consistency in clustering. The direct distance between any two DAG is granted to be less than or equal to the sum of their distances through an intermediate DAG. This property is critical for avoiding paradoxical results and ensuring valid clustering behavior. With the GED measure, String2 clusters DAGs based on structural similarity by K-means algorithm. Instead of attempting to compute an average graph, which is computationally infeasible, we introduced the concept of the similarity center. The center graph is defined as the most frequently occurring data flow DAG, identified through graph similarity search across all DAGs within a cluster. To accelerate graph edit distance computation, we adopted the A* plus LSA algorithm. This approach optimized the GED calculation by using a best-first search strategy, prioritizing paths with lower estimated cost to find the optimal transformation efficiently. Additionally, local structural analysis is integrated to refine the search space, allowing for faster identification of edit operations specific to data flow DAGs, such as operator type and edge direction modifications. Finally, we introduced the experimental performance of String2. We used two different workloads, Nesmark benchmark and PQP queries. String2 is compared with three automatic parallelism tuning methods. DS2 is a representative method based on the linearity assumption between operator parallelism and processing ability. CounterTune is a Bayesian optimization-based method that tunes the parallelism of a string job using its own tuning history. 02 employs zero-shot learning to construct a cost model for data flow level performance prediction. Using this cost model, 02 determines the initial parallelism degrees for a job. To simulate source rate fluctuations, source rate varies over time. Overall, String2 achieves the lowest recommended parallelism across various string jobs. CounterTune generally outperforms DS2 by employing Bayesian optimization to incorporate the tuning history of the target query. For PQP queries, 02 consistently recommends the highest parallelism, as its optimization focuses solely on minimizing data flow performance metrics without considering resource efficiency. And in most cases, String2 requires less number of reconfigurations, because it leverages global historical data from similar data flows, combined with the GNN to capture operator-level bottlenecks, which make its reconfiguration action more accurate. The above experiments are conducted on Flink. As to timely data flow, the experimental results are similar. String2 recommends smaller parallelism while maintaining the processing ability. We also compared the performance of the fine-tuning model. Because SVM and XGBoost meet the monotonic constraint, the recommended parallelism is better than that of neural network. Overall, our experiments show that SVM is slightly better than XGBoost. As shown in the figure, we also analyzed the computational overhead of the online tuning and offline pre-training phases. Thank you all for your attention. I hope this presentation has provided valuable insights into our work on String2, and we will be happy to answer any questions or discuss further details about our research.